Alright, so is everybody done? If you're still working on your peer grade, that's totally fine. You have until midnight. But did that work for everybody? Was anybody not able to find the peer grading or no issues? Everybody was able to open the .py file? All good? Alright, cool. Yeah, I don't know if you guys think that's a good idea or if you think it's a bad idea, just let me know, because, you know, peer grading can be a little stressful, especially if you don't think you graded your person fairly or whatever. Part of the reason why I'm totally okay with peer grading for this class is because it is pretty chill. The homework is just kind of for fun, so I hope the peer grading is also just kind of chill for fun. Okay. So today we're going to go over first class functions. We're going to talk about the call function. Has anybody ever written a dunder call function? No? Sweet. Okay. So if you haven't finished your peer grade, that's okay, but I would just go ahead and close your computer anyway, because we're going to just carry on. And like I said, you have until midnight, so no need to continue doing the peer grades now. So functions are objects. We've kind of mentioned this offhand in the past couple of lectures, but today we're really going to dig into that deep. It turns out there's all sorts of cool stuff you can do because functions are objects. You can assign them to variables, you can call methods on them, you can pass them into functions, and return them to functions. So, oops, wrong direction. Alright, I'm still getting used to this thing. So here's an example of setting a function to a variable. It's as simple as just making any variable. The main difference here is that usually we're used to seeing functions paired with a set of parentheses. And when you put those parentheses on that function, then that means you're calling that function. In Python, if you leave those parentheses off, then what you're doing is you're just referring to the function itself. And that's an object, and so you can assign it to a variable. And it's kind of weird to see, but it works just like any other variable assignment. And now, since this variable is a function, we can put a set of parentheses on it. And calling this function now will call the function that we assigned it to. So we get 2. 2 is the mean of 1, 2, and 3. And now we can reassign this variable to a new function, call it again, and we get the other result. So it's really just like any other variable, except the value is a function, and you can tack parentheses onto that value. And by tacking parentheses on that value, you're calling the function. Similarly, since functions are objects, you can call methods on them. And this is different from calling the function. We're not putting the parentheses on the function itself, we're calling a method on the function itself. And then we're calling it. And so it turns out functions, because they're objects and all objects have an equals method, functions have an equals method. So we can check to see if func is still equal to sum. And it is right now. In fact, they're not. It's not just equal to sum, they're the same thing, because they assign those variables. We can call string on a function. And in fact, that's what's happening every time we are printing out a function, which we'll do a fair amount. That wasn't me, but it's reminding me that it sounds quite fun. You can pass functions into variables, or into functions. So print is a function, and we can pass a function into it as a parameter. And so here's an example of where this method ends up getting called, because print is going to try to cast the thing that you pass into it as a string. So by doing that, it's going to call this method right here. And then it gets printed out just like we expect. And just like how we can pass a function into a function, we can return a function from a function. So here we're going to write this function. It's going to take in a num, and we're just going to check if that num is 0. And if it's 0, we're going to return mean. Again, no parentheses. We're returning mean itself. Otherwise, we're going to return sum. And now if we call this function, we have to call it in kind of a weird way. So we tack on these parentheses here, and we're calling this function. We pass in a num. And then we passed in 0 here, so num is equal to 0, so we return mean. So the result of this expression here, everything up to that parenthesis, that is now mean. So to call mean, we now have to tack another set of parentheses on. So when you have functions returning functions, you can end up with these kind of like sets of parentheses all just one after another. And that's because the result of calling one function is evaluating to another function. So it's a little weird to look at, but it's just because this function is returning a function. And we get what we expect. Questions about this? I'm thinking like one question.
Well, so converting the method to a string is the built-in function sum. How do you print out just the name of it as a human readable form?
So like just like if you wanted to print out just the name of like here func is sum,
Yeah.
and you're saying we wanted to like print out the fact that func is really just sum. That's a good question. It turns out that most objects and most classes in Python have an attribute called .dunder_name. And so if you wanted just this name, the name of the function itself, you could probably access it with the .dunder_name. But I'm not sure exactly if you would access it on sum or the type of sum. Probably just on sum. Yeah, let me know if that works. It looks like you have a question on it a lot. So.
It's just dunder_name.
And it worked? Cool.
So what if you make your
Yeah, go ahead.
what if you make a function and then you like have a variable set to that function and then modify that function?
Oh, great question. So variable assignment in Python is basically by reference. And that's because really what we're doing here, this variables in Python are really just names that refer to a thing. So assigning func to sum here, and then if you were to change sum, you would also be changing func.
So then is it possible to do like a dot copy or something?
That's a great question. I don't know if you can do a dot copy on a function. But you have to remember that you don't change functions very often. Like, usually a function, once it's defined, is kind of almost immutable. That being said, I think you can change a function, but I really don't know if there's a copy method. That I don't know. Good question, yeah.
I just
Oh, really? Okay.
change one to do.
Yeah, it's hard to change a function, but yeah, it would change it for both. And that's just like how it is for other immutable data structures in Python. So like if you're going to assign a name to a list and then change the original list, then the name that you assigned that list to would also see those changes. Yeah. Other questions? So it seems kind of weird, right? Like in this scenario, obviously this is pointless. Like this is really pretty meaningless. Like why is this num? In what scenario do we really want a function to return either mean or sum based on whether a number is 0 or not? Like that makes no sense. But it turns out this is actually useful. So here's one scenario where I've actually used this. Let's say we've got this init function, and we're just going to print init. And then we're going to have some variables called count and state. And then we're going to set the count to 0 and set the state to inc. So what's inc? Inc is this function. We print inc, we have some variables, increment the count. And then we set the state to output. What's output? Well, output is this function here. It's got some variables, and we're going to output the count. And then we're going to set the state to end if the count is greater than 10. Otherwise, we're going to set the state to inc. And what's end? Well, end is this function, and we're just going to raise a stop iteration. So what the heck is this here? It's pretty weird. This is a state machine. State here, we're always assigning state to some function. And basically what this is saying here is set the state to output, as in next time, do this, change states. Change the state to this. So you can think of that as an arrow. In this scenario, each one of these functions is a state. And calling that state will change state to the next state. So this is a state machine. And then you would run the state machine by setting state to init, and then, while true, calling state. Then you catch a stop iteration. So, and this works. And I kind of wish I had included what gets outputted, but it's exactly what you expect. It goes init, inc, outputting, inc, outputting, inc, outputting, inc, outputting, and then eventually it just stops. So again, this is still kind of a contrived example here because this state machine doesn't do anything, it just counts up to 10. But if you've written a game, or if you've done some embedded programming, then this pattern might be familiar to you because state machines are really useful for dealing with programs that go through different views or different states, obviously. So, like for example, if you're programming a robot that's trying to go through a maze, one state might be everything's okay, move forward. But another state might be like we've just hit a dead end, so turn around. So you have these different states, and it's really convenient when you can represent the states themselves as functions, and then you just call the function, and the function is responsible for doing this manually. You might be able to imagine if we couldn't do this, if we couldn't set variables to functions, then the way you would have to implement this is with a ton of if statements. And you would have a state variable that's just an int. And you'd have a switch statement like, oh, if state is 0, then we know that means it's an int. And so I actually call this function. If state is 1, then we know that's inc, call this function. But because we can just set these functions to variables, it's very, very clean. No need to interpret an int or anything. Questions about this? Oh wait, what? No, there should be a question about this.
It seems like there'd be significantly better ways to represent state machine.
Yeah, so there are state machine classes and things. And if you're building a big state machine, you should probably use one of those. But for every, big class that you bring in that deals with things, that's a dependency that you might have. So for lightweight things, I think this is a pretty good pattern. But yeah, if you're building like an actual robot, like, hundreds of states, yeah, there's probably a better way to do this, but it does work. And for small state machines, that is change the volume.
Yes, you did.
Oh, this is so cool. For small state machines, that's really, really pretty sweet. Other questions? I think 2 more questions.
Can you talk a little bit about how global works?
Yeah, so okay, that's the other question I was expecting. So the reason you have to say global here is that in Python, if you assign to a variable, it's going to try to assign that variable in the most local scope it can. So like in that init function, if I hadn't said global count state, then setting count equals 0, that just makes a local variable. And it wouldn't be visible in any of the other functions. So that's the other reason why this solution is pretty bad, is it's creating a bunch of global variables. And you can tell by the number of times I had to say global. So you would definitely want to wrap this into a class or something so that these variables are actually fields of some object, something like that. Yeah.
Are operators objects? Can you do this with operators?
Great question. Yeah, so operators, an operator like plus maybe, or like this operator here?
Like if, else, global, while.
Oh, you mean like control?
Those work too, like equals, greater than.
Yeah, so I was going to say, so operators like less than, greater than, plus, those are all actually just syntactic sugar around calls to methods. So like this count variable here, despite being an int, is an object, and it has a method dot less than, dot greater than. So those are functions too, yeah, but it's just with the syntax it doesn't look like it. The question of whether an if statement is a function and is an object, that's pretty interesting. At a certain level it is, but not at the same level as a function. These are not if statements and for loops and that kind of thing. They're not functions, but they are objects to the interpreter. And it turns out that Python actually reveals those objects to you. So you could actually get a reference to this if statement, but it wouldn't be a function. It would be a node in the abstract syntax tree, and we'll get to that later. Okay. So here's another application I've seen. This one I saw at work over the summer. And it's where you have a class, and in that class, you represent the things that the class should do as a list of steps, where the steps are functions. So here, this instances of processor have this steps list, and this steps list is references to methods. And then you define one kind of actionable method here, and that's, we named this class processor, so we better have a process method. And that process method is then just going to loop through those steps and call it. And this is cool because it works really well in combination with inheritance. So let's say we wanted to take this processor, but instead of adding 1 and then adding 2 and subtracting 1 and add 1, we want to do all that but then subtract 1 more time. We could make a 1 less processor, and then with no extra work, call the super constructor and append another step. And now, without having to redefine the process method or anything, our 1 less processor is going to actually subtract 1 at the end. So this is a really nice pattern if you can represent some process as a series of steps, and those steps all take the same arguments, or even if they don't. It's really nice for specializing processes. And so the way I saw this over the summer was these processors were actually tree visitors, and each tree visitor had a certain things that it was supposed to do to each node. And then there were special versions of that tree visitor for certain special kinds of trees that needed to do extra steps. And so those steps would just get appended to the list. But the interface for dealing with the visitor was exactly the same. It was always just this visit method, this process method. I mean, that never had to change. Questions about this?
So I guess this saves you from having to copy paste the, like if you just wrote that out as a list of instructions in Python rather than a list of functions, you have to kind of copy them over to the class.
Oh yeah, like you're saying, if we didn't even have these methods at all. Yeah, without these methods, I mean, you would have to copy and paste this code basically. And obviously, this is a simple example, so that wouldn't be such a problem. But if each one of these steps is actually a whole program, whole set of files that does this complex processing, definitely don't want to be copying and pasting that. So it's nice to be able to just represent it as a list, and then you can change the list later. Yeah.
You also just have a process method in one less processor and call it super process and then whatever steps you want.
Call super process and then whatever steps you want. That's true, but then you're specializing this process method, and you have to make sure to call super process method, and that may or may not jive well with other subclasses. So here the advantage is that you can be very explicit in representing your specialization as just a modification of this list. Whereas if you were to override the process method, then you're being a little less explicit. You're adding steps that aren't in the steps list. And you would have to actually, if you wanted to see what the steps were for a given class, you would have to go and trace through every single process method. Whereas here, you just print out the list. Yeah, good question. Other questions? All right, cool. So, if functions are objects, what's their type? Function, yeah. But if function is a type in Python, that means there's got to be a function class out there. And if there's a function class out there, how does it work? Like, how does it get this special ability to have parentheses tacked onto it? That's kind of cool. But it turns out that Python exposes it in a method called dunderCall. And it turns out any class can be a function just by defining the dunderCall method. So let's take this example. This is exactly the same reverse function that was in the first slide set. And it had problems, and we identified those problems, but just copying and pasting it, it works exactly the same. We can rewrite that function with a class. And then inside that class, we write the dunderCall method, and we do exactly the same thing. And now, to use our new version of this reverse method, we instantiate our class. Now we have an instance of our class. And then that thing is a function. So we can call it. And it works exactly the same. So what do we do here? We made a class that's kind of similar to function. We made a class whose instances are callable by implementing the dunderCall method. We could have done this on one line by tacking these parentheses onto result, constructing our instance of reverse. And so this is another scenario where you get these weird, chained calls. Because you have one set of parentheses to instantiate your class, and another set of parentheses to then get in this call method. I don't need to jump anywhere, I just to get in that call method. So questions about dunderCall so far? Mm-hmm.
So, somewhere in the Python libraries, there's a class called function, and it has defined call. How do you define the first call?
Great question. Yeah. If there's a function class out there and it defines this call method, then
Call is a function.
then what is this thing? What is is this not an instance of function? But we're writing function. If our call method, dunderCall is a method, right? And methods are kind of like functions. And there's a class function. There's a class method too. How can we define the call method in the method class? It's kind of like, well, something has to be the first thing, right? So, if we get the type of reverse, we get function, and that's kind of what we expect. If we get the type of other reverse, what do you guys think? What do you expect?
Reverse.
Yeah, obviously, because this is just an instance of this class that we just called. We just instantiated it. We better get reverse, and yeah, we do. What's the type of other reverse dot dunderCall? Method. Because call is a method on this object. How about this though? Type of capital R reverse dot dunderCall. Function? Yeah, it's function. Because this is an example of what I was talking about the past couple of classes. This is a static reference here. Here we were referencing .dunderCall on an instance of our class. Here we're referencing .dunderCall on our class itself, which actually gives us a static reference to that method as if it were a function. So if we were to try to call this thing, we would have to then put in self manually. Okay, so that makes sense, right? Because a method is something that's bound to an object, and a function is something that isn't. So that kind of makes sense. Now, what about this, though?
So let's see, function. Reverse is a function. So it's
Well, first of all, do we even know that this thing exists?
no.
Wait,
I mean, it
reverse
should.
is a function, and function has a call method.
Yeah.
Right?
Does it? I mean, we don't know.
It might be
It
that.
must be a method.
I mean, I made it sound like the class, the function class, has a call method, because that's how I introduced the call method. But maybe the function class is actually some special thing written in C. Well, it turns out reverse is a function, like we saw, and it does have a dot under call method, and its type is method wrapper. Okay. So that's a little weird. It's a little weird for this thing to have a dot under call in the first place, because we think of functions as kind of like a fundamental building block. And so for it to have a method dot under call, like what are we calling? Are we calling the function or are we calling this method? Like what even is this? What is method wrapper? Well, let's investigate further here. If we could call this thing, but it had a method dot under call, and we can call this thing, then why maybe this has a dot under call? And it turns out it does. It's also
Meta.
and you can do this as long as you want. You could in a while loop, like just keep accessing the dot under call method over and over and over again. And you'll always get an instance of method wrapper. And it turns out this is where you get into C land. Method wrapper is an interpreter entity that is kind of handles this like chicken and egg problem. Something has to actually be like a function call in C at some point. Well, that's this thing, and it wraps methods and functions so that they actually do something at the end of the day.
So why is it called method wrapper and not function wrapper?
Good question. I don't know. I think it's probably because this thing is a function, but functions are objects.
So it's an
And so technically this is a method. So you could maybe argue that Python only has methods because at some point you get to method wrapper all the time. So functions are really just fancy methods on themselves. But that's a good answer. Other questions about this?
So reverse.call is a method wrapper.
Reverse.call is a method wrapper, yeah.
So what does calling reverse.call?
I think it does this. I've never actually tried though. That's something you could pull up a Python shell and try on your own. I think it does what you would expect when it calls the function. Other questions? All right. So okay, that's fun. But is this useful? Because here, we put this function into a class, and now we get to take in self, but we didn't touch it. So this is kind of pointless right now. But it turns out that taking in self is actually pretty useful if we want to make a function that has state. So before, I made functions with state. The state variable was called state, so you know that it has state. But that state those were just global variables. So that's not great. So if you want a function with state, it turns out a really great way to do it is to wrap that state as an instance variable in your class that is now callable. So if we have an inc class, this thing is going to be an incrementer. It's going to increment. And we're going to have some data, our self.num. And then we're also going to implement call. We're going to increment num and return. And so now if we make an instance of inc and call it, first time we're going to get 1. But the next time we're going to get 2. So at a glance this looks pretty weird because we think of functions in a mathematical sense as being kind of like the same thing every time. It's just an immutable, pure function, as they say. But here, because of our ability to actually make our function an instance of some class, then that class can have some state. So this is a very non-pure function. But it's totally allowed in Python, and it's a great way of encapsulating function state without making global variables. Does that make sense? Questions about this? So one application of this is if you want a function that has a cache. A cache is state, it's memory. It's something that we have to keep in a variable somewhere. And without this ability, we'd have to keep that memory just as a global variable somewhere. But because we can actually make our function really an instance of a class, then we can keep that memory in our class field, as a class field. So the classic example of a cached function is Fibonacci. Let's make it a class called fibsolver. And the very first thing we're going to do is make some memory here, and we're going to remember that the fib of 0 is 0 and the fib of 1 is 1. And now in our call function, we're first going to check if this thing is in memory. Otherwise, then we're going to actually compute the fib. So now if we make an instance of fib solver, we call it fib, we can call fib just like it's a function, just like we had some Fibonacci function. But that Fibonacci function would be linear time if we were just going to compute this whole thing every single time from scratch. But now what we have is actually a pretty clever fib function that's going to remember every single time you call it. So not only is this if you've taken algorithms, this is a dynamic programming solution to fib. So this will run in linear time. But this is actually better than that because it's going to run in linear time the first time you call it, and then constant time after that. So if you were to call fib of 1,000,000, it's going to take on the order of 1,000,000, it's going to take a while. But then if you call fib of 1,000,000 again, it's going to take constant time because it's going to still be in that memory dictionary. And it's going to be there until we replace fib with another instance of fib solver.
So what are the advantages of overriding a call as opposed to just defining a new method?
Great question. So the question was like, why do we need to make our instances callable versus just having a method that's more descriptive, maybe? That's a great question because often if you find yourself implementing call, you end up regretting it later and you end up just changing it to a function with a name like calculate fib, or like we could have called this calculate, and then down here we would have said fib.calculate. That makes sense too. But so I think that using dundercall is good if you want to be able to hide the fact that there is state. So here, Fibonacci is not a function that necessarily needs a dictionary. But we kind of want it to be there and for the user to not have to think about it. So here by using dundercall instead of some other method name, we've really hidden this dictionary. I mean, fib looks like just a function here. But it's not, so we know it's an instance. Yeah.
I think I just thought of a situation which actually would be useful. If you had like a list of, if you had a heterogeneous list of both functions and then callable objects.
Yep.
Yeah.
So that's another, and we'll actually see an example of that later.
So this might be something that we're going to talk about later, but is there a way to apply this kind of caching construct to any function? Like you just pass in a function and it gives you a cached version?
Yeah, we'll talk about that later.
I tried doing like max dot call. If you use it, it still uses just max or whatever function you're using, but the pointer is different each time. So maybe it's like just traveling through those calls before actually calling the max. I'm not sure.
The what is different each time?
The pointer of the function.
Interesting. I don't know. It's possible that maybe every single time you tack on a new .call reference, the Python interpreter is actually spinning up a new method wrapper instance for you. Yeah. Okay. Questions about this? I know this is a little, that's a beast of a line. If you haven't seen it before, Python has this great string method called .join. And anytime you want a comma-separated list, you're going to want to use comma.join here. The number of times I've written a for loop to go through a list of things and concatenate that thing with a comma, unless it's the last time, it's such a hassle. And then I learned about this and so I'm addicted. So we'll see that later. Okay. This is just kind of for fun. What's going to happen here? So we said a function can return a function, right? And self is now a function because it's an instance of this callable thing. So what if we return it? Then if we call func, we get a recursion object just like we expect. But we can call that, right? So it turns out you can just tack on as many parentheses here as you want and you're always going to get exactly the same thing. So that's just kind of for fun, but I don't think that's really useful at all. But you can do it. Okay, and so there's one other way to write functions in Python that I want to talk about, and that's lambdas. Now, lambda is nice and simple. Here we have an add5 function, and it just returns the number plus 5. We could have written that like this, with this lambda function. And what you do is you just say lambda, and then the name of the argument you want to take, and then you write the expressions that you want to be the result of the function. So this doesn't work for things that are multiple lines. You can't write a multiple line lambda. But if you write a function that just has one line and returns the result of that line, then it's likely you could have written it as a lambda. Not that you should, but you could have. So here, you don't have to write return or anything because it's just one line, but this means that the result of this lambda function is num plus 5. And we can call that lambda just like we can call a function. If we get the type of add 5, we get function again. And if we get the type of that, what do you guys expect? It's a function. So there's no separate type for lambdas. Not that that's important, but. So, okay, now that we know how to write a lambda, there's a bunch of cool stuff you can do with lambdas. And these are used all the time in Python. I think they're probably the most used example of the usefulness of the fact that functions are objects. So here, we've got a function called map. And map is going to map a function over some iterable. So here, I want to string concatenate the numbers from 0 to 9. But Python has this weird thing, it's kind of annoying, but if you try to string.join things that aren't strings, it's not going to work. So we need to manually convert everything in this range to a string. So how are we going to do that? Well, the most intuitive way would just be to write a for loop over that range. Convert each of those numbers into a string and put them in a list or something. But then we're writing a for loop just to call str on a bunch of things. And that's kind of like, it's a whole for loop for just one function call. Well, so it turns out map is perfect for this. You just map the function that you wanted to call in that for loop over the thing that you were looping over, and this will do it for you. And so now this will actually work. String is a function. String is the function that we were calling before to cast things to strings. So we can map this function over this iterable, and the result will be what we would have gotten by writing an actual for loop. We can write our own function in line here. So, here we had to have this function. What if we didn't have what we wanted? What if we wanted to convert it to a string after having added 5? Then we can write this lambda expression here. What's going to happen here? Anybody guess what's going to be printed out?
0 or 1 on whichever lines. Also use map object.
So there are a couple ideas. Turns out that this is going to print out a map object. And the reason for this is that Python and its map implementation is lazy. So one of the advantages of doing things like this is that it's only going to map this function over this iterable if we actually demand something from this map. So here we've said, okay, be prepared to map print over range 2. But we haven't actually asked it for anything. We've just said, be prepared to do this. So here it's saying it's prepared now. But that's probably not what we wanted. So if we wanted to actually see the result of the map, what we can do is we can cast this thing as a list. A list on an iterable, it's going to demand things from that iterable and put them in a list. And so now we're actually going to get something. But what's going to be printed? Guesses? 0 and 1.
Result going to be like a list of none, but it's also going to print 0, 1.
Did you run it? Or did you? Oh, okay. I was about to say. That's exactly right. So this is not going to work how you might think. It's going to map print over this range. And print is going to print out the range. So we're going to get a 0 and a 1. But what is the result of calling print on a number? None. Yeah, it turns out Python every function in Python returns something every time. But print we think of as void. But like I said, Python has no void functions. It always returns something. Turns out void functions in Python return none. And so mapping print over this range is actually going to result in a list containing none, none. So we're going to get the prints, but then we're going to get none, none. So this is an artifact of the difference between functions that do things and the functions that return things. So print is not a return thing. So it doesn't really make sense to map a void function over a thing. So that's map. I wanted to go over sorting. Oh, whoa, that went fast. So I wanted to go over sorting because that's another example where lambdas are really useful. And then there's filter. Filter is basically like map, but instead of mapping, it's like a if statement. So you can represent ifs in that for the filter. And then I was going to go over reduce, but man, this example was really weird. So I don't think it's actually that useful. But this was my other example of a call method where it's really nice to be able to just pass this thing. And then if we wanted this thing to have statement for that thing to be a callable, makes a lot of sense. So if you were curious about that, there's that. So anyway, functions are objects. This homework is going to be kind of cool. I think it's pretty fun. The last part is unintuitive and maybe tricky. But it's not, despite it represents exactly half the tests I wrote, but it is not worth half the assignment. So I just wanted to say that. And then also, if you're really stuck, you can Google it and you'll see it. But I think it's a worthwhile thing. I threw it in. It's fun.